I never gave this course before in IMPRA, so I will start following a little bit in the beginning the course, how it was done by André Nachbin. So it's, by the way, probably the way how you can see the Portuguese version of the course, because he has the YouTube videos as well. But at that moment, I think we will depart. So I don't think I will be giving exactly the same course. But the content in general is the same. So there will be a big section dedicated to numerical linear algebra. In various aspects, so it's analysis of matrices, solving equations, finding eigenvalues, and so on. And this is probably the basics of most computation, So usually numerical analysis in one or the other form reduces to the problem of numerical linear algebra. That's why this is a very important topic from practical point of view. So it is, that's why researchers put attention that everything works very well and very optimal in this part. Then the second part is has to do with essentially with the relation between the numerical representation and the original mathematical representation. So this is approximation theory. So this theory essentially tells you how you represent more general mathematical objects in numerical form. Right? So that certainly, because we cannot represent, for example, the real number in exact numerical form, because the real number has infinite number of digits, like an irrational number. So how to approximate it numerically? So and it's even harder with the functions. So it will include various aspects. So it's interpolation. Then there will be a question of calculus. So how to compute derivatives, the integrals, and so on. And then we will also touch this important piece, which is called fast Fourier transform. So the Fourier transform is very important operation in many applications, and it's much used in numerics due to existence of this fast Fourier transform. So there is this object. We will learn what it is. So then there will be third part is the numerical nonlinear systems. So here essentially it's a classical Newton's method. So the question of how you solve nonlinear system of equations. So this is a important complication from a linear algebra where everything is linear, approximation where you just represent. So now we solve equations which are non-linear. And the next step is even harder. So it's a numerical integration. Numerical integration of differential equation. Equations, and here I think here we will put most attention to ordinary differential equations. Ordinary But I also plan to discuss some aspects of partial differential equations. So you see, it's every step is more complex. We will start with something very basic, very elementary, especially today. But then it will become continuously more complicated. I think mathematically it's not so complicated subject, but it's important that you learn how to implement it. So we will have two pieces. One is theory, and the both sides, both parts will be used in evaluation. So we will make tests. There will be theoretical tests, and there will be numerical tests. So it's programming. Programming. So essentially, we will see how you numerically implement different algorithms, and I myself is mostly used with MATLAB. Yeah. But so for me, it will be easier if you do it in MATLAB or learn. It's actually quite a simple thing to learn. I can even maybe devote, if you need, devote some class for to see how it works. But anyway, if you learn to program in different language of this class, like Python and so on, it's okay. So I will ask you to know how to do that, and I will be posting all the information in my web page. So there will be my web page is HTTP. I think nowadays it's HTTPS. Well, I don't remember how it. You never write it, right? So it's a web page. It's let's see, impa.br, and then you go to teaching. In the teaching, you have the information of all our courses, of all my courses. So what I was given, not all, there was some loss of information, but usually I put all information about my courses in this web page. So it will be updated along with the time. Okay, so what we do, so today I will show you a few problems which lead to numerical linear algebra, and to see what are the obstacles that you can find in this problem, and what are the reasons for having, well, why we need essentially numerical tools. So simple problems. Idea of these problems is to show you how you convert some simple practical problem to the language of linear algebra, and to see that this language of linear algebra is rather universal language how to treat many different issues. So what we will be considering is a traffic. So the first example will be traffic. Cars traffic. So imagine two streets going from north to south, and from west to the east. So we have blocks. blocks. And we'll just consider two streets. So simple system. So how we have it here, one street goes one direction, another goes another direction. So let's put direction down here. Up here. And then it will be left, right here, and left here. So we want to somehow control the traffic, knowing some, having some information. So what is the idea? That we monitor traffic in certain places, and we want to know what is the traffic in the other places. So that's the usual problem, and that's useful for many reasons. For example, for constructing parking places, or, for example, if you want to close one street for the renovation, what will be the change? So will it be a disaster around or not? So the problem is formulated is that let's measure what is the flux, or what is the traffic of the flux of the cars outside, and try to see what is inside. So this is, let's say that there will be flux of the cars. So this is north, so it will be N1 entering, N2 exiting. Yeah, so this is, for example, each number is how many cars pass in there per unit time, per hour, during the day. Then there will be S1, S2 cars exiting. It's west, so it's west W1, W2, and this is east, E1, E2. And then, so we assume that this is given, and we want to know what happens inside. So we know the data outside, so what is happening inside. So we give variables here. So there will be x1, x2. Put it here, x2, x3, x4. So how you form? What would you do in order to find these four fluxes? If you know the fluxes outside, so you, essentially you need to define the balance equations at road crossings. Right, so you have four crossings, 1, 2, 3, 4. And you know that in the road crossing, usually you can disconsider how many cars is there. So how many, as much cars enter, as much exit. So we can just simply balance influx with outflux. So they should be equal. And we can do it for each of the crossings. So the first crossing, what we have? So what exit, so influx is, and let's do it. Okay. So influx is N1 plus W1. And out is correct, yeah, X1 plus X4. So in the second crossing, what enters, It's okay. It's okay. So it's no problem. Okay. So second, let's try like this. In is x1 plus x2. Out is n2 plus e1. The third is in is e2 plus s2, and out is x2 plus x3. And then the last is entering x3 plus x4. And exiting s1 plus w2. So there is this system, and now so it's already a system of linear equations. So now we know that we usually like to write it in a matrix form. So we put all the unknowns to the left. Actually, let's just change the order. So this is the system, and now we can write it in a matrix form by writing the matrix. So matrix, it will only have unit entries, so it will be 1 and 4. So it will be 1, 0, 0, 1, and this will be multiplied by x1, x2, x3, x4, and equal to, so the right hand side is n1 plus w1. Then it will be here 1, 1, 0, 0. Here will be 0, 1, 1, 0, 0, 0, 1, 1. And 2 plus E1, E2 plus S2, S1 plus W1. Should be okay. So it's already directly the linear system of equations. Right? So we have vector of unknown, vector of data, input. So this is what we measured. We know what we know that what are the fluxes outside, and we need to find this vector, these fluxes in the inside the in the inner block. So this is unknown. And also we already see that it's in principle a fair game because it's 4 unknowns, 4 equations. So now what you can do is now let us take first equation and substitute it. You see, we have 4 equations. So in principle, we can take first equation and subtract the other ones from it. So it will not change solution, right? Because we don't change number of equations. We don't essentially we just transform the equation. So let's take the first equation and try to simplify it. So let's subtract the second. the third, and the fourth. So when you do it, you see, when you subtract the second, you cancel the first component. When you subtract, or you can look at this system. So when you subtract the second, you cancel x1. When you subtract the third, you cancel x2. No. This should be, this is minus, this should go with plus. So we subtract minus this plus this minus. Yeah. So then it goes with plus, then x2 is canceled, then x3 is canceled, and then x4 is canceled. So everything will be canceled here. So it will be, and then put it in the place of the original equation 1. So what will stay is that it will be 0, 0, 0, 0. Other equation we keep. Here what will be? It will be just the same vector. So and here it's n1 plus w1 plus third vector, so plus e2 plus s2 and minus all of this. So it's n2 plus e1 plus w1 and the same. So this is a transformation which preserves the solution. So you can think a little bit and see that actually whenever x is the solution of the first, it's solution of the second. Whenever it's solution of the second, it's solution of the first. So it's a equivalence transformation. So we didn't change these solutions. But now what we see that the first row is 0. So it's identically 0. So it means already a conclusion that solution exists if this vector is 0. Something is wrong. This is wrong. 2 here. And this is a very natural condition because this condition just tells you that as much cars enters, as much have to exit. So in a stationary situation, in this model, assume that there is no accumulation. Right? There is no parking, for example, that just absorbs the cars. So as much enters, as much exits. And so what you see, N1, W1, S2, and E2 are all influxes. So sum of the all influxes should be equal to the sum of the outfluxes. But then we can set x1 arbitrarily because equation for x1, you see expression of x1 is no, not x1. Then we have 3 equations for unknowns. Because the first equation is identically zero, which means that there is non-unique solution. So we already have different conclusions which come from just the same original assumption is that we have a test for the data that everything is okay. So you can test that the data that came is correctly by checking that this inequality is equality. If it's wrong, that what you receive is not correct. And then also you know that, unfortunately, even though you checked fluxes at 8 points outside, just to compute 4 fluxes inside is not enough, right? So you cannot define x1, x2, x3, x4 knowing all the fluxes outside, and the reason is why? Interesting, why? No? Is it correct? Yeah, it's correct. So this is exercise. So think why it's not enough. So what happens inside such that knowing what enters, what exits is not enough to determine what is inside. Actually, this is a different example for with what I considered before, because if you consider this street going right and this going left, then there will be a circle here. And then it's clear why. Yeah, because if you have a circle inside, there could be any number of cars just going in a circle. That's why you cannot define what is exactly here, because you can add any number of cars which will go just in a circle without affecting what is outside. But in this situation, this is a little bit more sophisticated. So this will be good exercise for you to see why there is we cannot what happens inside such that we cannot solve the problem. And of course this is can be generalized. So this is just two streets. So whenever you make a plan and want to control the traffic in the whole city, there will be hundreds of streets going in one direction, hundreds of streets going in another direction, a huge number of intersections. So, but anyway, the strategy will be the same. You can define balance, and you can also define other components like sinks or sources, which is so there can be flux due to the parking lots and so on. But anyway, you come up with a matrix with a vector of unknowns, vector of data that you somehow can monitor, and the big matrix which stands at the side. So, and you need to solve a big system of linear equations, which should be already maybe thousands and so on. And a very similar problem you get. So this does not need to be traffic. This can be any other problem, and the very similar problems you have in different situations, which essentially reduce to the solving a system of linear equations. Ax equal b, where x is a vector, A is a matrix, and B is a vector. So this will be one part of numerical linear algebra that we will address. But not all. Okay. In principle, you see, in principle, this picture not only shows you how to solve problems with this type of fluxes, but in some sense, the way how you solve differential equations. So, for example, partial differential equations or ordinary differential equations, they can be solved in somewhat similar way, because at the end you have to discretize your equation, putting a mesh. So there will be certain points at which you know the value of your variables, and you have certain relations between these variables, which are represented by some kind of fluxes. So at the end, almost in all situations, you end up with a system of linear equations that you have to solve. And this can be, in some situations, which from practice it can be matrix 1,000 by 1,000, million by million. Sometimes it's you have billions of unknowns, and you have to solve it fast. So even though computers are fast, but you need to solve it fast and efficient. Okay. So then another nice example that was I also took from Andre. So it's about the adjacency matrix of a graph. So what happens here? Imagine a graph which corresponds to the result of a game. So take your favorite game. So there will be 4 players. And we will draw the arrow from the one who won to the winner to loser. Winner to loser. Okay, so let's do it like this. So A won. A is a winner with B. A is a winner with C. Let's say like winner like this. Let's say that this one as well. One, well, arbitrarily. So what you can see is that the situation is complicated, right? So how you rank them? Who is the first? Who is the second? So how to rank? So how the linear algebra comes here? So we need we first represent this as a matrix. So as a matrix, so what we do is so this is the play. So we put four columns, 4 rows, and the first row will be data of the first player, the second row of the second player, third of the So each row corresponds to the player. And the number that we will put here will depend whether he won or not. So they don't play with themselves, so this is 0 on the diagonal. But then we will put the unit if it won. So A won with B and C. So it's 1 here and 1 here, because this is also A, B, C, D. But lost playing with D, so 0. Okay. So B lost from A and C, but won with D. C only has a win with B. And D lost with B, but won with the others. No, so it's 1, 1. It's good. So A like this, B 0, C is winning with B, and D is winning with A and C. Correct. So now how to rank. So how to rank, the idea how to rank is what we will compute. We will count direct and indirect wins. So what means direct? Direct win is just direct, so A won B, so we will put 1 to this. Yeah? But also there is indirect win. For example, A won B with B, but A also won with a C who won with a B. So there is an indirect win. And the same is, I think I made it in such a way that it's, for example, you see C lost with D directly, but won indirectly. Yeah, so this, let's assume that we want to count all of this. So it turns out that A computes direct wins, but in order to compute indirect wins, so direct wins are controlled by A, and indirect wins, it's the wins that you made through the intermediate person. So they are computed with matrix squared. So check. Check that when you compute A squared, you get directly indirect wins. So the total wins that in our count will be given by this sum, A plus A squared. So let's compute this matrix. So A squared, remember how to compute square of the matrix, so you should multiply column by the row. So the first will be column by the 0, 1, 0, 0. Then the second will be sum of these two. 1, 0, 0, 2. Then the third will be sum of the 0, 1, 0, 1. And then the last will be this one. Let's just check that it's correct. So, for example, I don't think it's correct. Yeah. So, for example, it tells us that, for example, it tells us that D has 2 indirect wins with B. And let's check it. So D1 with B in this way and also in that way. So okay, correct. So there are two indirect winds. So this is just our strategy how we want to compute winds. So, and then let's take a sum, and it will be 0, 2, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 2, 2, 0. And then we can compute the total winds for everyone. So A, the play A has 6 winds. The play B has 3 winds. The play C has 2 winds. And player D has 5 winds. So what's wrong? 4 winds here. Yes. Good, thank you. You see? So we can rank them. So this is first place, this is second place, this is third place, this is fourth place. I tried to make A to win, but turned out that D won. You see, so this is you see this is very not very intuitive strategy, which turned out that D won despite the D had 2 direct wins and A had 2 direct wins, but because of the indirect wins, D was the first and A was the second. So that's a way. So this is another way how you see with the linear algebra by multiplying matrices and so on. You can check complicated things. Of course, for the players, it's relatively simple. But there are many problems with the graphs which are complicated, and graph can be huge. So the matrix will be very, very big. So you come to some algorithms which gives you in algebraic language some direct answer. So that's and certainly we need numerical schemes to see how it works. Well, so this is all with this simplified example. So now let's do something more serious. And especially, well, slightly more serious. So the next topic is the Gaussian elimination method. Well, I'm used to give a very short break. Of course, I was late today. But let's make a very short break for at most 5 minutes. So it will be break till 2:28. Okay, and then we will be back. So just take coffee and then just relax a little bit. let's continue. So now we know that we need to solve linear system of equations. How you solve the linear system of equations? So what we need to draw a path for constructing a numerical method. So it means that we need to make a solution in the form of the algorithm. So let us. So what I'll explain is the Gaussian elimination method. Gaussian or Gauss? I think Gauss elimination. Gaussian elimination method. So this is very basic. I think one of simplest ideas of linear algebra. So it and it has essentially it has two steps. So the first, in order to understand how we do, the first consider the for solving linear systems, the systems of linear equations. So what I will. So let's first start with certain simple forms. So first, let us see that it's easier. First, let's see that it is easy if a matrix has a triangular form. So let's say upper triangular, upper. And it's essentially this the same for lower triangular form. So for example, the matrix has a structure A, 1, 1, and Y, 1, 2, and 1, 3, 0, A, 2, 2, A, 2, 3, 0, 0, A3, 3. And then x1, x2, x3 equal b1, b2, b3. So this is upper triangular matrix. Because you see that if you select a diagonal, so all non-zero elements are on the diagonal or upper part. So in the same way, if it's on the diagonal in the lower part, it will be lower triangular matrix. So how you solve the equations for the upper triangular matrix? It's a direct way, which is called back substitution. So what you assume? We assume now that all diagonal elements are non-zero. So what you can do, you start with the last equation, x3. So a3 3 by x3 equal b3. So you find x3. Right. When you know x3, you can solve the next one because only x2 will appear. So there will be x2 by a22 plus a23 by x3 equal b. So you move this element to the other side, and then you find the solution as, so it will be b2 minus this product 8 to 3 x3, which you already know from the previous step. And then you have to divide by the diagonal element. And then finally, you do the same with the last equation, x1, because x2, x3 you already computed. So it will be b1 minus n1, 2, x2, 3. You divide everything by 3. So this is back substitution. So you see what you do, you start with the equation which has just one element, so you can directly solve it. And then you back substitute it in the next line. Solve it, back substitute in the next line. So you can, certainly you see that you can do exactly the same algorithm whatever size of the system. So if it's 100 by 100, you can just do it in the same way. And the exercise for you, just check that a similar strategy works for lower triangular matrices. So if everything is below, you can just do the same, but you start from the opposite end. So you first do x1, then x2, then x3, and so on. So whenever the matrix is upper or lower triangular, everything is okay. So the question is for a general matrix. For the general system, AX equal B. So with B n-dimensional and matrix A n by n. So what Gaussian elimination method does is that we first reduce a system to upper triangular form, and then solve by back substitution. Which sometimes is just done in a single process. So now the question if what happens if we have other elements here? So what would you do? So essentially what we do, we assume two operations. One operation is so how would you do? So let's just do it first in explicit form. And then generalize. So first assume that A11 is non-zero. So if it's 0, then just check other elements. Because what you can always do, you can just sweep the equations, right? So you just take, if this is 0, you just choose the one which is non-zero and just change these equations. Just change these rows. It will work. So that's why we can assume that first is non-zero. So what we can do is that since it's non-zero, we can substitute the equation 2. We can substitute, let's not draw this. We can substitute equation 2 by what? So by equation 2, so we can subtract equation 1 with the right coefficient. And we take this coefficient m1 to be A21 divided by A11. So what will happen? The first equation will keep the same. So when we substituted the first with this coefficient, we cancel this element. So here will be 0. And here will be A22 with a tilde, A23 with a tilde, x2, x3. So the first we didn't change the B2 with tilde. So now we can compute what it is. So A2 with a tilde, 2 with a tilde is the one that was before. And then we subtract it with this coefficient, M1, A12. Then A23 with a tilde, it will be A23 minus M1, A13. And then B2 will be just the same. So B2 is B2 minus M1, B1. So what we did is we put 0 here. So next step is you can do exactly the same operation with the third equation. So you substitute E3 by E3. So that better it's not good. It will be M2. M2, 2. So minus M3 E1. And in the same way, we choose M3 to be A31 divided by A11. So just in the same way, you get 0 here, and then you stay with the certain new numbers on the other places. So this is what Gaussian elimination means, that we choose some equation and we eliminate other elements of the matrix. Right? So after we did this, what happens is that first equation you don't touch anymore. So we already made use of the first equation, and in the remaining part is smaller. You see the first column is 0, so it becomes 2 equations with respect to 2 unknowns. Right? So, with a matrix which is 2 by 2. So you can just do exactly the same operation. So you choose the element which is non-zero. If it's 0, you can just sweep the equations. And again, make it the same operation in order to put zeros to all everything below. So you can just 0 you have to put this element to 0. And when you do it, if the matrix is bigger, you do it every time. You do it many times. Every time the matrix with which you work is smaller and smaller and smaller until you do it until the end. So at the end, you will end up with exactly upper triangular matrix. And when you finish with the upper triangular matrix, you have explicit solution. So this is how you solve the system of equations. So this is an algorithmic method. And essentially, it's based on two operations. It's based on two operations. So the first operation is for any equation I, you can substitute. So operations. So any equation I can be substituted by this equation, but plus any number lambda multiplied by any other equation. So any lambda, and j not equal to I. So this is what we did for the elimination. So we was subtracting or adding, so it doesn't matter. It's just what's the sign of m. So we were substituting the equation by the same equation, but with added or subtracted another equation with arbitrary prefactor. Then remember that whenever we had to check that the first element, the upper element is not 0, and if it's 0, we have to switch the rows. So this is second element, second operation that we need. We can substitute one row by another row, but then so we just sweep two equations. Just change the number, renumber, put a different numbering of equations. And in fact, what we didn't use, but in principle, it's also useful for numerical purposes to use. You can just take any equation and multiply it by any constant, which is not 0. It also doesn't change. So usually these three operations can be used. And now we can see that essentially what we did by multiple operations, by using this multiple, we can just describe this operation in the form of the matrix. So in Gaussian elimination, so let's see what this operation means. So we had a matrix A, X equal B. And now we substituted. So after this operation, we obtain a new system with where. So what it is? So. Let's write it the direct way. So let's take, for example, this operation. So we take E2, we substitute by E2 minus M E1. So the original system, which was this 3 by 3 matrix A by X equal B, the new equation is what? So we can just multiply everything by a new matrix M. So the AX B. So we will multiply both sides by the square matrix. So the first equation we don't touch. So remember, yeah. So if you multiply it with this row, then it exactly preserves the first line, right? So this is the first line. So this first equation we don't touch. The second equation, so we should subtract E1. So we put minus M, 1, 0. And the third equation we do not touch, 0, 0, 1. And we should do it the same here in order to preserve solutions. You see, so what we do is Gaussian elimination. Gauss elimination. In principle, it's a operation which it can be represented by the multiple as multiple operations of the form A. Instead of AB, you substitute them by MA and MB, where M is certain upper triangular matrix. No, lower triangle. So you see that every matrix that we use is a lower triangle. So essentially, Gaussian elimination is a sequence of the multiplication of this pair of the matrix and the right-hand side by a matrix which always lower triangular. So in other words, what you do is you take matrix A and B and send it to the matrix. So you do it multiply. So you take M1, M2, M operations that you need to total some certain number of operations, total operation for the Gaussian elimination by A, and the same M1 by B, where this you can, and you can say that this is, okay. Okay, so call it M. So what we have at the end is as MA equal. So after we do all operations of Gaussian elimination, we end up with an upper triangular matrix. So this is upper triangular. And this is lower triangular. Yeah, because product of lower triangular matrices is a lower triangle. So at the end, you can just say that A is M minus 1U. And M minus 1, you know how to invert product. So you have to invert every one and put them in opposite sequence. So it will be M1 minus 1, M2 minus 1, M minus 1, U. So we call this matrix L. Will be equal LU. So it remains to see what is this L. So now observe that if this is a matrix M, So if matrix M, like I, has this structure, which was 0, 1, 0, 0, minus M, 1, 0, 0, 0, 1, then Mi minus 1, so let's put Mi. Then inverse matrix, you can just compute what it is. It will be, I guess, I just try to guess. I would guess that this is this, no? Let's see. No. 1. So this is inverse matrix, also lower trigonal. So both direct and inverse operation of the Gaussian elimination is represented by lower triangular matrix. So this is lower triangular matrix. So what we have is that we represented A as a product of lower and upper triangular matrices. And this is what is called LU decomposition. So you see that by using algorithmically the Gaussian elimination, we come to the representative of the matrix A as a LU decomposition. And essentially, this is what you do. You first, by eliminating the elements, you construct the upper system with the upper trigonal matrix, and lower the trigonal matrix defines this elimination process. So at the end, another way to represent a solution would be, so what you have of A x equal B would be to use this decomposition. So instead of just making the Gaussian elimination explicitly, so we know that Gaussian elimination proves that you can always represent matrix A as a product of lower upper trigonal matrix. So if you know how to compute L and U, so in particular, we know how to compute with the Gaussian elimination, but there can be different ways. So then what you can do, you can, another way to represent a solution, you can say that, which was the numbers? So you can, so you see it's LUX. So let's UX, let's say that this is Y. And then the original equation will be LY equal B. Right? So this will be LUX equal B. It's the same. But now we have two equations, which is upper trigonal, upper, and this is lower trigonal. So both of them can be solved by back substitution. So you see that this already gives you, starting to give you the taste of the numerical linear algebra, because we made a certain transformation of the matrix, which in fact can be done in different ways. And you can already seek for the way which will be more optimal. So more optimal from point of view of the number of operations. So this is important issue. So how many operations do you need in order to solve this, to make this decomposition? So it's what is called complexity in the nonlinear linear algebra. And then whenever you have these two vectors, and you are given the right-hand side, you know how to directly find the solution by back substitution. So there are two equations, one with U, another with L. So first you solve for Y with back substitution with matrix L, and then you solve with back substitution with U. So this is a way how it can be done. Oh, I think we're done. We were a bit slow, but this is because I was late. Okay, so we continue. I think I'll be maybe first, second week we just continue, and then I will start to give exercises. So exercises I will announce, of course, in a class, but I'll be putting them all in the web page. So see you Wednesday. Thank you.